Section 7.6 is about solving radical equations. Right? Again, the most important section in any college algebra or algebra class is almost always going to be when we get to the point that we solve equations. I mentioned that back in Chapter 6, and we're mentioning that again here in Chapter 7. So now that we know all of the techniques that we need to know for simplifying radicals, whether it's pulling out perfect powers or using rational exponents, and all the techniques we learned for multiplying, dividing, adding, and subtraction. Now that we have all those tools in our mathematical toolkit, we are now ready to answer the algebra question of, if I've got a relationship between variables, an equation that involves radicals, how do I solve that equation? How do I find the missing piece, the missing value? Okay. Now once we do that, we're going to be able to answer some application questions as well. So we're going to throw all that together in one section here. And let me just remind you that the strategy for almost every type of algebra problem where you're solving an equation is to somehow reduce it down to a type of equation we already know how to solve. And that's exactly what we're going to do here. We're going to reduce radical equations down to equations that don't have radicals anymore. And there is a technique that allows us to do that, that gets rid of the radicals. Okay? So let's talk about how we do that. The steps for solving a radical equation are as follows. We got 6 steps we're going to go through. The beginning step is to isolate a radical expression on one side. Get the radical by itself. If there are more than one radical, choose one and get it by itself. Then raise each side to the power of the root index. If it's a square root, you're going to square both sides. If it's a cube root, you're going to cube both sides, raise both sides to the third power. Once you do this, that gets rid of the radical that you have isolated, and you combine like terms and you simplify. If there are still radicals after the first 3 steps, say for example that you had 2 radicals in the equation, the first 3 steps will eliminate one of them. So in order to eliminate the other, you will go back and repeat steps 1 through 3. You do this until there are no more radicals, at which point you have a type of equation that you already know how to solve. It may be rational, it may be polynomial, it may be linear, but you have techniques for solving all those types of equations now. So step 5 is to actually do the solve. Go back to those previous techniques and finish the solving of that equation. And then you want to check for extraneous solutions. You'll remember from Chapter 6 when we covered rational equations, we had to check and make sure that none of the answers were excluded, meaning that made the denominator 0. In this case, because the domain of radical functions has to be where x is greater than or equal to 0, it's possible that the solutions that we get after we eliminate radicals aren't actually answers that we can evaluate in the problem, meaning that they might plug in here and make that negative. So what you do to check for extraneous solutions is you plug the answers back into the original equation just to see if they satisfy it. So at the very end, the last step is to actually check your answer. And you need to do this, you're required to do this, because it is possible that your answer, or one of your answers, may not be an actual solution to the problem. Okay? The technique of steps 1 through 5 can produce all the possible solutions, but may also produce additional solutions that we call extraneous. The rest of this section now is just going to be a series of examples where we work out a solution to radical equations following those 6 steps that we just saw. Okay? So let us begin by looking at this problem and walking through those 6 steps. First step, if you'll look back in your notes, was to isolate a radical expression. So in this case, the radical is by itself already. Step 1, done. Step 2, raise each side to the power of the root index. So what's the root index here? That is a 2, right? It's understood to be a 2. So I'm going to come in here and I'm going to raise both sides. I'm going to have 3x plus 4 equals 8, 3x plus 4 under the square root, and I'm going to raise both sides to the second power. Okay, now the square root and the square cancel each other out, and I'm left with 3x plus 4. No radical on the left-hand side. On the right-hand side, I'm just going to take 8 times 8, which is 64. Now we have managed to eliminate the radical, and this is a simple problem to solve. We simply get x by itself because it is a linear equation. So subtract the 4 across, we have 3x is equal to 60. Divide both sides by 3. That leaves me with x is equal to 20. Okay? Now we come over here and we check our answer. Okay? That is, we plug 20 back into the original equation to see if it actually works. So square root of 3 times 20 plus 4, is that equal to 8? Well, simplify this. You end up the square root of 3 times 20 is 60 plus 4 is 64 equals 8. That checks. So this is, in fact, our only solution. Now let's look at example B. By the way, I didn't finish my list here, but this was step 2 where we got to this point here. Step 3 was to simplify. We didn't have to do any of that. Step 4 was to repeat if necessary. We didn't need to do that. And 5 is where we got here. And this was step 6 over here. I'm not going to write that down every time, but just so you have an idea of which steps were being applied at which phase of that solution. All right, example B. Step 1 is to isolate the radical expression. So here's the radical. We need to get it by itself. Okay? In fact, I'll highlight. We're going to get this expression by itself, so we need to take the 7 and move it to the other side, right? So I'm going to subtract 7 from both sides, and I end up with the square root of x minus 1 is equal to negative 5. Okay? Now I can keep going from this point and solve and get all the way down to where I check my answer again. I'm going to learn that this is extraneous because I can look at this expression right now, or this equation right now, and tell you there is no solution. Now how do I know there's no solution? Okay, square roots are always positive, right? We learned that in a previous section. So it's impossible to have the square root of something equal to negative 5, so we will always have no solution if that's the case. Okay. Again, let me emphasize that maybe you didn't catch that and you just went through, you squared both sides, you solved for x, and you got a number. You will actually get an answer. If you plug it back into the problem, you will see that in fact that does not actually solve the problem. So you're back to no solution. In example C, we have that the square root of 6x plus 7 minus x is equal to 2. Step 1 is to isolate the radical term. So I'm going to add x to both sides. That leaves me with the square root of 6x plus 7 is equal to x plus 2. Now in order to simplify, to get rid of the radical, I need to square both sides. I'm going to take this and raise it to the second power, and this and raise it to the second power. On the left-hand side, square and radicals will cancel. I'm left with 6x plus 7. Okay. On the right-hand side, I have x plus 2 times x plus 2, which you'll remember you always have to FOIL whenever you have a binomial squared. So I end up with x squared plus 4x plus 4. Now this is a little bit different than the previous examples in that we end up with now a quadratic equation to solve. So to solve quadratic equations, we have to get it equal to 0 and factor. So I'm going to begin by let's move everything to the right-hand side since the x squared term is over there and it's already positive. As a general rule, I always move things to the side of the quadratic equation that has a positive x squared term. So it makes it easier to factor that way. Subtract 6x from both sides and subtract 7 from both sides. End up with 0 on the left-hand side. On the right-hand side, I'll have x squared minus 2x minus 3. Now I factor. That's going to be x and x. I know it's a plus and a minus. 1 and 3 are my only choices, and since the negative 2 is negative, I'll put the 3 on the negative and the 1 on the positive. I think that works. Minus 3x plus x is minus 2x. So that is correctly factored. So I have x plus 1 equals 0 and x minus 3 equals 0. That leaves me with x is equal to negative 1 and x is equal to 3. Now I have two answers that I have to check. So let's start with x is equal to negative 1. That means square root of 6 times negative 1 plus 7 minus a minus 1, does that equal 2? Right? I'm just plugging this back into the original equation. So that gives me a square root of negative 6 plus 7 is positive 1. And that's a minus 1 is plus 1. That's 1 plus 1. That does equal 2. So that one checks. I know this is a solution. Alright, let's try the other one. X is equal to 3. That's going to give me the square root of 6 times 3 plus 7 minus the number 3. Is that equal to 2? So I have the square root of 18 plus 7 is 25 minus 3 equals 2. So it's 5 minus 3 equals 2. That checks. So it is also a solution. Both of them solve the original equation. Alright, we're done with that one. Let's move on to the next one. In example D, we have the square root of the quantity x plus 5 minus the square root of the quantity x minus 3, all is equal to 2. Now our strategy is still the same. We want to get rid of the radicals, but because we have 2, we're going to have to get rid of them one at a time. So we begin by choosing one we're going to isolate. So let's start with just say the first one, right? That makes the most sense that we're going to isolate this. So we're going to take this radical and move it to the other side. Okay? So that means I'm going to add that whole radical, square root of x minus 3, to both sides. That leaves me with the square root of x plus 5 is equal to 2 plus the square root of x minus 3. Alright, so now we square both sides. Square this and square this. On the left hand side we have all of a square root squared, so that cancels and I'm left with x plus 5. On the right hand side I am squaring a sum, so you have to remember that that means to FOIL. 2 plus the square root of x minus 3 times 2 plus the square root of x minus 3. You can't just square each separately, each term, right? You have to actually do first outside, inside, last. So I have 2 times 2 gives me 4. The outside and the inside both give me 2 square roots of x minus 3, so that's plus 4 square roots of x minus 3. Right? That's the outside and the inside. Like I said, both of them is 2 square root of x minus 3, so added together is 4. And then the last terms together is the square root of x minus 3 times the square root of x minus 3, which gives me just x minus 3. Alright, it's the same as square root of x minus 3 squared. The radical cancels. Okay. Now at this point we simplify by collecting like terms. So on the left hand side that's completely simplified already. On the right hand side I can combine the 4 and the 3. I'm left with 4 square roots of x minus 3 plus x, and 4 minus 3 is plus 1. Now I'm going to isolate the radical term again. I've finished step 3. I still have a radical in there, so I start back over at step 1 and get this radical by itself. So subtract x from both sides. I'm going to subtract 1 from both sides. The x's actually completely subtract out. Those are gone, so 5 minus 1 is 4 is equal to 4 square roots of x minus 3. Divide both sides by 4, so the radical is completely by itself. I have square root of x minus 3 is equal to 1. The radical is by itself, so now I can square both sides. I have 1 is equal to x minus 3. Add 3 to both sides, and x is equal to 4. Okay, now I'm ready to check. Is x equals 4 the solution? So plug that back into the original problem here. So I have the square root of x plus 5, so that's 4 plus 5, minus the square root of 4 minus 3. Is that equal to 2? And I think it's going to be. So square root of 9 minus square root of 1, that's 3 minus 1 equals 2. That checks. So x equals 4 is the solution. That solves that equation. And we were able to get there by canceling out the radicals one by one. Well, the most important step that you need to remember, at least the one that's easiest to forget, is this FOIL step right here. If you're going to square something that has a sum in it, you have to FOIL. You have to do the distribution rule completely. All right, two more examples in this section. Example E, I wanted to do one that has something besides a square root involved. And also just a quick refresher back to rational exponents. We have 2x minus 3, the quantity, raised to the 1/3 power, plus 3 is equal to 0. Okay, so the first thing you need to realize, what does 1/3 power mean? You've got to recognize that that, as we've covered before, is the same thing as a cube root. So this is the same problem right here. I've got a radical involved, so I'm going to have to get rid of the radical. I begin by isolating that radical term by subtracting 3 from both sides. I have the cube root of 2x minus 3 is equal to 3. Negative 3, in fact. Now I'm going to raise both sides to a power that cancels the radical. So far, that's always been a square, right? So we squared both sides. Now it's a cube root. So we're going to raise both sides to the 3rd power. So take this to the 3rd power, take this to the 3rd power. A cube root cubed cancels out, and I'm left with just the radicand, 2x minus 3. Okay, negative 3 cubed, negative 3 times negative 3 times negative 3 gives me negative 27. Now I've got just a linear equation, no radicals at all, so I just solve by isolating the x. So add 3 to both sides. 2x is equal to negative 24. Divide both sides by 2. X is equal to negative 12. Okay, let's double check our answer. If x is equal to negative 12, I'm going to have the cube root of 2 times negative 12 minus 3 plus 3. Does that equal 0? That's the cube root of negative 24 minus 3 plus 3. That's the cube root of negative 27 plus 3. That's negative 3 plus 3, which equals 0, which is exactly what we wanted to do. So that's correct. And there you go. All right, let's do one last example. The type of application problems we're going to be primarily looking at in this section are ones where a formula has already been derived and you know certain parts of that formula, but you've got a missing value and you need to solve for that unknown quantity. As in this example, we've got a function here that serves as a model for the number of Americans living alone in millions X years after 1970. So we can figure out an estimate of how many Americans are living alone since the year 1970. F of x is that number living alone. X is the number of years since 1970. According to this model, can we find out when 29 million Americans live alone? And we'll use our calculator to estimate using a decimal approximation. So 29 million, that 29 is the value in millions, so I'm going to put a 29 right there. 29 is equal to 2.9 square roots of x plus 11. So I'm going to solve for x. That's going to give me the number of years since 1970. I can figure out what year 29 million Americans lived alone. Now we just go through those 6 steps. We got an equation here that involves radicals. We go through our steps for solving. We isolate the radical, so subtract 11 from both sides. We end up with 18 is equal to 2.9 square roots of x. I'm going to divide both sides by 2.9. I'll use my calculator to figure that out. What is 18 divided by 2.9? Gives me roughly 6.2069 equals the square root of x. If I square both sides, I'm going to get x is equal to 38.5, which rounds up to 39, right? So that means 1970 plus 39 years means that should happen in year 2009. All right, and that's the end of section 7.6, solving equations involving radical expressions.